All right, let's dive in. Today, we're going to connect two incredible things: the super complex camera you carry around inside your head and the huge, colorful world out there. It's a journey that takes us from biology all the way to physics, and trust me, it explains some of the most amazing things we see every single day.
I mean, have you ever just looked up at the sky and wondered why? Like, why is it blue? Or how do sunsets get those incredible reds and oranges? And what's the deal with stars twinkling? You know, these are questions we've all probably asked at some point. And believe me, the answers are way cooler than you might even guess. And the key to unlocking all these mysteries? Well, it actually starts with a piece of gear we all have right here, the human eye. It's so much more than just a window, you know? It's this incredibly advanced living camera that does amazing things with light. So let's start right there. We're going to take a look inside this biological camera and figure out exactly how it all works. You know, the way your eye works is shockingly similar to a camera. It's a really great analogy. Your iris, that's basically the aperture deciding how much light gets in. The lens right behind it does the focusing, and the retina way at the back. Think of that as the digital sensor, the part that actually captures the picture for your brain to deal with. Okay, so let's follow a little particle of light on its journey. First up, it hits the cornea, that's the clear dome on the front, and that does a lot of the heavy lifting, the first big bend. Then, whoosh, through the pupil. After that, the lens makes tiny adjustments to get the focus just right. And here's a wild thought. The image that actually hits your retina is upside down. Yeah, it's your brain that does the incredible work of flipping everything right side up so the world makes sense. Amazing, right? But here's the thing. Your eye isn't just a simple point-and-shoot camera. Oh no, it's way more dynamic. It's always adapting, and its ability to change focus is just, well, it's one of its coolest tricks. This superpower is actually called the power of accommodation. You've got these tiny little muscles in your eye, ciliary muscles, and they are always working. Look at something far off, they relax, and your lens gets flatter. Now look at something up close, like your phone. They squeeze, making the lens rounder to bend that light more. The best part? You're doing it this very second, and you don't even have to think about it. Now, of course, the system isn't always perfect, right? Sometimes the light focuses a little too early, in front of the retina. That's what we call nearsightedness. Or it focuses too late, behind the retina, and that's farsightedness. And, as we get older, the lens just isn't as flexible, which leads to something called presbyopia. The good news is we have a pretty simple fix: corrective lenses. Different shapes, like concave or convex, can fix these issues perfectly. Okay, before we jump into the physics side of things, I just want to share one really powerful number with you. 4. Just 4. That's how many people can get their sight back from a single pair of donated eyes, from the cornea specifically. It's such a simple thing, but think about the impact. It's just incredible. All right, so we've got the biology down. Now let's totally switch gears and talk about the physics of light itself. Let's talk about the stuff our eyes are actually designed to see. So this all kicks off with a concept called dispersion. You've seen this, right? When you shine white light through a prism, out comes a rainbow. The prism isn't making the colors, it's just splitting the white light up and showing you what was inside all along. It was Isaac Newton who first figured this out, which is pretty cool. And what you get is the spectrum we all learned in school, VIBGYOR, right? Violet, indigo, blue, and so on. The whole reason they separate like that is that each color's wavelength bends just a little differently. Violet light gets bent the most, and red light gets bent the least. It's just a basic rule of how light works. Okay, now let's take this up into our atmosphere, where two really important things happen to light. First, there's refraction. That's when light bends as it goes through layers of air. Then you have scattering. That's when light rays get bounced around and deflected by tiny particles in the air. So just remember this: refraction is bending, scattering is bouncing. Got it? Those two are going to be super important. Okay, and now it's time for the big payoff. We're going to take all this stuff we've just learned about our eyes, about light, and we are finally going to answer those big questions we started with. First up, the big one. Why is the sky blue? Let's get one thing straight. It has nothing to do with the air being blue or a reflection of the ocean. Nope. The answer is all about that one word: scattering. So here's what happens. When sunlight hits our atmosphere, the tiny molecules of air are just the right size to scatter the shorter wavelengths of light, which happen to be blue and violet. They scatter them everywhere. The longer waves, like red and yellow, they just kind of pass right on through. So when you look up, what you're seeing is all that scattered blue light coming at you from all over the sky. And that's exactly why in space, where there's no atmosphere, the sky is just black. No scattering, no blue. Okay, so if blue light is scattered all over the place, what's going on with sun raises and sunsets? Why are they red?
Well, think about it. At sunset, the sun is low on the horizon, so its light has to travel through way more atmosphere to get to your eyes. And on that long journey, almost all of the blue light gets scattered away before it even reaches you. So what's left? What makes it all the way through? You guessed it, the longer wavelengths, the reds, the oranges, the yellows, and that's what gives us those beautiful sunset colors. All right, last big question. Why do stars twinkle? It's so poetic, but it's not actually the stars doing it. It's our atmosphere again. And for this one, we need to talk about our other key concept, refraction. See, stars are so incredibly far away that their light comes to us as just one single tiny point. And as that little point of light travels through all the swirling, turbulent layers of our atmosphere, it gets bent back and forth, back and forth. That's what we see as twinkling. But planets are much, much closer, so they aren't just a point, they're more like a tiny little disk. Even though the light from them is also getting bent, all those little fluctuations just average themselves out, so they look like a nice steady light.
And get this, here's one last mind-blowing trick that atmospheric refraction plays on us. It actually bends sunlight over the curve of the Earth. What that means is we can see the sun for about 2 minutes before it actually crosses the horizon at sunrise, and for another 2 minutes after it's already set. Our atmosphere literally gives us 4 extra minutes of daylight every single day. How cool is that? So when you put it all together, it's this beautiful dance, isn't it? The biology inside your eye and the physics of the sky all working together. They take simple rays of light and turn them into the amazing, colorful world that we get to see every day. And that kind of leaves you with a final big thought. That whole rainbow of colors we can see, that's just a tiny, tiny sliver of all the light that's actually out there. I mean, all around us, right now, are radio waves, microwaves, infrared, things our eyes just can't pick up. So it makes you wonder, right? What other invisible worlds are all around us, just hiding in plain sight, waiting for a different kind of eye to see them?